This is problem for chapter 5. So we go for question 5.7. For stagnation boundary layer flow, U equal Kx, estimate the position Reynolds number where instability first occur. So the stagnation boundary flow here is a keyword, and another one is the instability. So the stagnation boundary layer here is actually when we have a boundary layer, but at the same time, it starts with the stagnation of the flow. So means that normally if we have a flat plate like this one, so we have a free stream velocity here, and then the velocity is not stopped, it's not stagnant, but the boundary layer will occur. However, if the flat plate is located vertical like this one, so if we have a free stream velocity here, so the molecule will once collide with the surface, so it will stop at certain uh, at a moment. So means that we call as a stagnation boundary layer. So after the collision here, so mean it start to develop the boundary layer. Okay, that is the idea of the stagnation boundary layer. Why? Because we need to choose a few numbers here based on the situation. Okay, and now to solve this problem, especially in chapter 5, we need to see these two tables. So I will provide the table in final exam or in test 1 and test 2. So I hope you could use the table properly. So one is table from chapter 4. Table 4.2, numerical value of the streamwise velocity for Fagner-Scan similarity flow. So, and then, as I said, we cannot use Blasius because Blasius is only for the flat plate that for the object which is parallel with the free stream velocity. But if we have a stagnation boundary layer, for example, means that the flat plate is now in vertical position. So we need to use the idea of Fagner-Scan. So means we develop the velocity based on the Fagner-Scan idea. So and then we have a table 5.1, spatial stability parameter of Fagner-Scan profile. So this is actually the guide, the hint or the data provided by Fagner-Scan previously from his experimental work, so we could take that number as our guide in our calculation. Because as I said in chapter 4, the research of boundary layer normally will use the idea of curve fitting. They will use the analytical, they will use the numerical and do the experiment, and later on they will get the curve fitting. They try to plot a simple graph, and then they will use that graph. They will produce equation from that data, and then next people will use that equation to predict the boundary layer. So this is the two table that you need to know. Okay, so we go to solve this problem. So because we know that the flow is stagnation flow, so I think we could refer to our previous lecture. So when the flat plate is located vertically, so the beta is equal to 1.0. So we look the table here. So we take we have a beta here, and then we found that we take the column for beta equal 1.0. So means that we need to take this data, this column. So and then to see whether it is stable or not, so we look at the stability here. So we found that if the beta is 1.0, so we take the idea of Reynolds theta critical. So and then you know that the Reynolds theta mean the momentum, so means that it's related to the movement or the energy changes of the flow. So and then because the delta star here is actually referred to the mass. Okay, so now the theta is the momentum. So we found that for beta equal 1.0, so we have the Reynolds theta critical is 5,636. So what we could say here is, okay, so at beta 1.0, which is the stagnation flow, it become unstable when Reynolds number theta here is equal to 5,636. 5,636. So and then we go for the flow of calculation is like this. So we take the value of theta star. So theta star can be taken from this table. So we have this table theta star, and it is equal of 0.29235. So we write down as theta star is equal to 0.29235, and then it is equal to the equation of the Falkner-Scan. So yeah, this you could refer from my my previous slide just now. So and then we could calculate this one. If you calculate this one, you will get we substitute the value of m equal to 1. So from where we could get the value of m equal to 1 here, it is come from this one. So in previous slide, in previous lecture, in chapter 4, so I give you the notes of beta is equal to m over m plus 1. So and then if the beta here is equal to 1, so you will find that the m also equal to 1. So and then we get m equal for 1. We substitute it here, and finally we could have this equation. Okay, so normally people will change the way we write the equation. Okay, we have a theta here, but we rearrange into theta over x. So when we want to write theta over x, so the term inside here will become ux over nu. So ux over nu, it could reflect as a Reynolds number. So and then we could write as this one. So theta over x is equal 0.29235 over Reynolds number, and then we could change into this one. Okay, so it is how to change this one. So it's based on this equation. So I think you could do this at home. For example, we have u, and we have capital U here and nu, and we have nu here, and then we have theta. So we just put the value of theta here. So we have 0.29235 with x over square root Reynolds, and then we find that ux over nu, okay, is actually the Reynolds number. I'm sorry, this is Reynolds number. So and then we could have this term. So I hope you could try this at home later on. And then the Reynolds theta here is now again equalized with this value. So we have Reynolds number 0.29235. Square root Reynolds is equal to 5,636. So then we could calculate the value of Reynolds number here. So and then we could get it is 3.717 times 10 to the power of 8. So means that the instability, so means that we could find, we could say that the laminar flow is start to turn, change into turbulent flow at Reynolds number of 3.717 times 10 to the power of 8. So in this situation, please bear in mind that we are not analyze flat plate, a normal flat plate of Blasius. We are analyze the flat plate which put in a vertical position, and then we the boundary layer will occur like this one. So we have a flow inside this one, and then we could predict that when the Reynolds number on this plate is 3 times 10 to the power of 8, so it start to show a sign of a turbulent flow. So this is the idea. So here again, if you see the symbol of Reynolds number. So we have the Reynolds number theta here, and then we have the Reynolds number x here. So please be careful when you write or when you answer this one. So we need to get value of Reynolds number x, because Reynolds number x means the equation is rho Vx or over mu, or rho VL over mu. So this is the symbol, the meaning of Reynolds number x. However, for Reynolds number theta here, so it's calculated as rho V theta over mu, means that the Reynolds number based on the momentum thickness. Okay, so you should understand that delta star, the displacement thickness, theta, which is the moment theta is momentum thickness. The unit is in meter. That's why the value of theta and also the value of delta star can be replaced in value of x or L here, because the value of x and L here is also in meter. Okay, that is the idea of this one. So means that from this calculation, we need to calculate the value of Reynolds number x here. So the x here mean the instability. So this is the assumption of the location where the transition between laminar and turbulent start to occur. So and then we do the same things for question 5.8. So and then here the question is for the separating Fagner-Scan wedge flow boundary layer, beta is equal negative 0.19884. Estimate the point x over L where boundary layer instability first occur. Assume a low subsonic Mach number. So here I answer this question by using the Reynolds number value, not the location. Okay, because I didn't found the total length of this one, so it is maybe a lack of point. So I just give you the Reynolds number. So here the word separating a Fagner-Scan wedge flow means that it's the flow, the situation like this. So for example, we have the incoming flow like this one, free stream velocity, and then the flow is start to jump on into this valley. So the idea of this one is means that we are purposely separate the flow, okay, by cutting the area at this one. So sometimes it's called the separating boundary layer. So and then the value of beta here is already so I think I give it one slide in chapter 4 saying that if we have a separating flow of Fagner-Scan, so the value of beta is negative 0.19884. So we use this in this question. So again, we are using the same table. Okay, so for example, we aim for the beta here with a negative 0.19884. So and then we have the beta here, negative 0.19884. And then the Reynolds number critical theta here is equal to 17. So and then from the Fagner-Scan table here, so the theta star is equal to 0.58544. So we write it here. So and then we do the same solution. So this is the solution, and then we could substitute with the value of m equal negative 0.09043. So you could calculate it by using beta equal to m over 1 plus m. Okay, so and then we could calculate this one, okay, using the Fagner-Scan, and then we get the value here, and then from this equation, okay, so and then we could get the value of Reynolds theta is equal to 0.8681 square root Reynolds x equal to 17, and then we could calculate that the Reynolds number of 384, we could predict, it is assumed that at Reynolds number 384, the instability start to occur. So means that the flow start to give a few sign of a turbulent flow on it. Okay, so we go for question 514 for stagnation boundary flow, boundary layer flow. So I hope you still remember the idea of stagnation. U equal kx, estimate the position Reynolds number where transition first occur using the method of Michel. Okay, so and then the transition, sometimes we could assume that instability means the flow start to show sign of turbulence. But sometimes in boundary layer research, we not take the instability starting point as the transition region, because sometimes it's still the situation is maybe the sign of turbulence is on and off. So sometimes it's disappear, sometimes it's appear. So we cannot say that that is the transition. So the transition region mean the location where the turbulence is start to occur continuously, something like that. So means that I hope you could understand the idea of instability and also the transition. So to calculate the transition here, so we will use the method of Michel. You could refer to the textbook equation 5.38. Okay, again, because we are doing stagnation flow, so the value of m, the value of beta is equal to 1, and then we could calculate the value of m, which is also equal to 1, and the theta star here is equal to 0.29235. So we could calculate by using this equation. So, and then we use this one, and this is the equation of Michel. So it is equal to okay, I'm sorry. So this is to convert from this equation into this one. So I hope you understand that here we substitute the value of theta here, then we could get the value of this one. So and then from Michel, the transition condition can be considered as this one. So this is actually an equation proposed by Michel. So we have the Reynolds number theta, it is 2.9, Reynolds number x 0.4. So and then we substitute the value of Reynolds number here, Reynolds number theta, which is this one. And then we get, now we only have only one Reynolds number x. So and then if we solve it, so we will find that the Reynolds number x is equal to 9.22 times 10 to the power of 9. So means that we can assume that the Reynolds number transition maybe can be assumed at 9.22 times 10 to the power of 9. So in some idea, we could say that the transition that give in this Reynolds number is maybe the condition where the turbulence start to occur continuously. So and then the idea of turbulence occur in boundary layer. Some researchers says that it doesn't mean that means that the percentage. So mean the maybe 1 or 2% of the total phenomenon of turbulence is start to it start to occur on that number. So and then again, we could solve this with another idea. So for example, if we use the idea of tweets. If you remember, so in last question in chapter 4, we have the convergent and divergent nozzle. So we calculate the location of transition, use the idea of tweets. So this is the equation of tweets. So and then we substitute the value of u here. So in this question, it is given that u is equal to kx. So and then we substitute the value. So we have this term 0.05, 0.075 over k. And then we substitute the value into the theta here, and then we could guess this get this one. So and then the Reynolds number here based on the on this one. So the Reynolds number theta is 0.274 Reynolds number 1 over 2. So please remember this term can be changed into Reynolds number. So and then okay, so you have ux over nu is the Reynolds number. So and then you need to add an extra x here. So mean you times with square root x over square root x to get this one. So means that I hope you could do this at home later on. So we could get the Reynolds number here, the Reynolds number theta, and then we substitute into the this equation. So mean we start with the twits, we use the Michel, and then we could get that the Reynolds number transition is occur at 1.764 times 10 to the power of 10. So if we compare these two values, so it is 1.7, 10 to the power of 10, and the another one is 9.2 times 10 to the power of 9. So we found that the number is almost almost similar to each other. So one is 9 times 10 to the power of 9, and another one is 1.2 times 10 to the power of 10. So it's still close to each other. So at this situation, I think it can both estimation can be accepted.